One application of the photoelectric effect is by making a photocell. So a photocell is a component you can put into a circuit that will allow you to control when the circuit activates depending on whether there's enough light. So you can set it so that the presence or absence of light will cause a circuit to kick in. So how do you build one? You start off with just a power source, positive and negative electrodes. If you have trouble can remember which ones are which, remember the acronym PANC, PANC, I don't know. Positive is the anode, negative is the cathode, and that the long thin one is positive, the little short stubby one is the negative. So to build a photocell, you start off with just a glass tube. Now we're looking down on this, but this is actually a 3D component, but we're looking down on it. So you start off with just a tube, make sure there's no air particles in there, we're in a nice vacuum, and you're going to have a corresponding positive and negative electrode inside. The can't quite pick it up. Let's just slide it in there. Oop. The positive one is kind of like a rod going down the center, or down the middle of the tube, and the negative one's the cathode is a little bit more complex. It's a kind of like the inside of a cylinder, or part of one, an arc of a cylinder, and it's coated with a layer of material that will photo emit when light hits it at whatever frequency you want it to photo emit at. So let's say you set up for visible light. Photon visible light will hit the material. Once it satisfies the work function, electrons will be emitted, and they'll be attracted to the positive electrodes. They'll cross the little gap in between, and therefore you'll get a current. We can use photocells for security systems, like you see in films. They're actually not as dramatic in real life because you can't actually see the light. So a more prosaic example might be the conveyor belt in your supermarket, the little laser at the end, and also automatic doors to control when they open or close. Okay, so we're going to have a look at X-rays because the production of X-rays is pretty much the opposite of the photoelectric effect. But just to remind ourselves what X-rays are, they're a form of electromagnetic radiation, very high frequency and highly ionizing. Okay, so how do we actually get X-rays? How do we produce them? We're going to start off with just a tube, and inside there's going to be tiny particles of air and gas and stuff. We want to get rid of them and create a vacuum, or as close to a good vacuum as we can, because we want nothing getting in the way of our electrons. So let's get rid of all them. Okay, that's just a tube. Later on down the line, our X-rays are going to be produced, and they're very ionizing, they're very damaging, and we want to control where they go. So we're going to put some shielding in place to protect the whoever's operating it and any kind of equipment that might be nearby. I've left a little gap here because our X-rays are going to go through them in a moment. Okay, so what we're going to need an anode. This is where the actual X-rays are going to be produced. We usually use tungsten. Very high melting point. That's going to act as our anode. And we're going to need some source of electrons. So we just have a filament. Run a very modest voltage through this filament, and you're going to get some thermionic emission going on. So some of the electrons that are part of this filament are going to be given just enough heat energy to escape, thermal energy to escape from the force of attraction holding them onto the coil, and they're going to be emitted. Now, left to their own devices, they're just kind of going to go around in all directions. We don't want that. We want them to target this anode. So what we do is we put another voltage, a very high voltage, between this part of the heating filament, which is now going to act as our cathode, and our anode. So we've created a very strong very, very high voltage between these, or potential difference. So that's going to cause these electrons that are emitted, they're now going to accelerate towards the positively charged anode at crazy speeds. So they're shooting along with that. Boom, boom, boom. Now most of them, the vast majority of them, will hit the anode, and their energy is just going to be converted into heat. That's one of the reasons why we use tungsten. It's got a very high melting point. But we're still going to need a kind of coolant system. So usually it's going to be oil that'll come in and bleed away a lot of the excess heat. So the vast majority of the electrons that hit the anode are just, their energy is just going to be converted into heat. That's not really what we're looking for. We're looking for X-rays. But every now and again, one will hit the anode and be its energy will be released as a photon. So this bombardment of the anode by electrons released from the cathode accelerated because the voltage between them will cause X-rays to be produced, which will then come off the anode, out through our aperture and towards the target. Now, X-rays, we want them to have different amounts of penetration. The higher the frequency, the more they're going to penetrate through matter. So if we want to increase the frequency of our X-rays, what we can do is increase the voltage, causing electrons to accelerate towards them. The X-rays they're produced will have a higher frequency. If you think back to when we introduced potential difference and voltage, we said that volts are defined as when you do 1 joule of work to bring 1 coulomb from one point to another. So the work done is equal to the charge times the voltage, just by rearranging that. So if you look at our situation where we're talking about how much kinetic energy would these electrons have, this is both for the production of X-rays and for the cathode ray tube. You can easily find it by just multiplying the charge on one electron by the voltage that's accelerating it. Let's look at some of the properties of X-rays before we look at what we can put them to use because of these properties. So firstly, they're ionizing, meaning that if they hit another material, they can knock off that material's electrons, making it charged. They can make something else an ion. They're very penetrating, meaning that they can pass through matter. So these first two properties make them very dangerous to humans because they can penetrate through you and affect the nucleus of your DNA, the nuclei of your DNA. Because they move as a wave, they're not a charged particle, so they don't experience any deflection when they go through a magnetic or electric field. If they hit a material that has a work function lower than their energy, they can cause photoemission. If they hit an emulsion, like a photographic emulsion, they can change it. That's why we're able to get a kind of take an image of an X-ray. And if they hit some materials, they can make them fluoresce or give out energy. And finally, again, because they move as a wave, they have some of the properties of waves. They can be diffracted or refracted, that kind of stuff. So now that we know some of the properties of X-rays, we can think about what kind of applications we can put them to. Now, you're probably familiar with the first one, which is using it to as an imaging tool in medicine. So you can use it to see what's happening inside someone, usually to see if a bone is broken. But you can also use it to detect if there's kind of diseased tissue there, because that might have a different density than the normal cells. And you can fine-tune how penetrating your X-rays are by altering the voltage of the tube that produces it, like we discussed earlier. So just to kind of comment on how this works, what actually happens is the X-rays on this plate, for example, would be kind of blasting through, and different materials will absorb different amounts. The more they absorb, the more white they appear, because what we're actually looking at here is a plate that was behind the X-ray. When X-rays hit it, it goes from being clear to being very dark and kind of black. So the black bits you see are where they're unobstructed. Nothing's gotten in their way, and the X-rays have just kind of powered through. And the white ones are where lots of those X-rays have been absorbed. Okay, so apart from imaging, we can also use it in medicine to destroy cancerous tissue. So cancerous tissue is when your own cells kind of rebel against you and reproduce out of control. And they're more vulnerable to being damaged by X-rays than normal cells. So we can use that to destroy them. And cautiously again, because X-rays can damage healthy tissue too. And finally, we can use them in industry for things like finding microscopic cracks or damage in materials that mightn't be visible to the naked eye, especially anything that might be vulnerable to like metal fatigue, that kind of stuff. Okay, to finish up and just to check, there's two questions you can try here. They're from page 30 and from page 22 of your exam papers respectively, and I'll talk to you soon.